Hello, everybody. Welcome to QDA Week 7, Lecture 6. This is where it gets confusing. This happens every year because we do one of these review sessions. So that wasn't really a lecture. So this is Lecture 6, but it's Week 7. You'll forgive me if I just confuse what number we're on for the rest of the year. Just wanted to remind everyone you can put your questions and comments in chat, of course, as we go. We'll try to answer questions as we work through the lecture. And I also want to remind everyone that there will be no lecture next week. There is no QDA lecture on November 3rd. We are having a reading week next week because your assignment is due on November 4th at 11:59 p.m. Don't try to push me for, can I submit it at 12:01 on Saturday? You can review the lateness policy from the Week 1 lecture if you have any questions or need any clarification on extensions or lateness. But yeah, that's your assignment that'll be due on November 4th, and thus we will have no lecture on November 3rd. Our lab is having some scheduled time off next week, so if you have any questions or issues, let us know about them as soon as you can. Replies might be a little bit slow next week. I remind you that the email policy for this class is that a response can take up to 2 working days to get a reply. You might be used to much quicker replies so far in the year, but that might not be the case next week with some scheduled time off. I will still honor the 2 working day policy, but if you email me on Wednesday night after I'm done working, Friday is not a working day for me, so I won't see your message until I start working again on Saturday. So please take that into account as you prepare your assignment and as you do last-minute writing. Try to get your questions to us as quickly as possible if they're coming up in the last minute. But that's enough about the assignment. Why don't we move on to today's lecture topic? Our main topic today is multiple regression, aka multiple linear regression. This lecture should very much be building upon what we covered a couple of weeks ago in the most recent lecture, simple linear regression, where we used one variable to make predictions about the value of another variable. Oh, my cat decided she wanted to start yodeling during the lecture, so hopefully you'll get to hear that throughout the class. Last time we did simple linear regression where you use the value of one variable to make a prediction about the variable of another variable. Multiple regression is the exact same concept, but instead of just having one predictor variable, you have multiple, and thus multiple regression. Hopefully this can be a relatively quick lecture because we covered a lot of the content in the last one. But that means we have lots of time for questions and answers. So if you have questions, throw them into the chat and try to cover them as much as we can. So let's flash back to a couple of weeks ago to our last lecture, simple regression. Last time we talked about a regression. We had a continuous variable as our outcome. That was the number of tweets that someone makes. In this case, it was like the number of tweets they make across several months. And we wanted to make predictions about that variable using some other continuous variable. So last time we used people's scores on an anxiety questionnaire as a variable that we could use to predict their amount of tweets. We talked about how in the absence of any other model, the way we might predict the number of tweets someone makes is just by guessing the mean number of tweets for every single person, just giving the same guess for every single participant. But if we have another variable like anxiety, we can start to build a new model, a regression model that helps us make different predictions for each person. And you might recall that if we wanted to figure out how good or bad our model is, if we want to determine whether our model is actually any better than the mean, we use the method of least squares. We wanted to determine how far above or below our regression line each point was. And we compared that to how far above or below the mean each point was. So we compared the model sum of squares to the total sum of squares, the total variance of our data set. Using those 2 measurements, we were able to determine our model sum of squares, our R squared value, and determine how much variance was explained by our model. And this lets us say whether or not our model is a better predictor than just using the mean alone. All of these concepts, all these things that we covered in simple linear regression will be all exactly the same this week. Even as we add more predictor variables, we're doing the exact same process of using variables to make predictions about some other variable and then comparing our models, seeing how good or bad our model was compared to simpler versions of the model. So last time our hypothesis was about anxiety, predicting the amount of tweets someone makes. Remember, when we're using regression, we're testing a hypothesis that one variable can be used to predict the value of another variable. That's where I was like highlighting and bolding and like sirens going off. Predict is your keyword with a regression. And that is just the same when we have multiple regression as when we have simple regression. So last time we were predicting that social media posting anxiety significantly predicts the amount of tweets someone makes. We ran a regression. We found evidence that supported our hypothesis. We used an F-test to tell us that our model was significantly more predictive than just predicting tweets using the mean alone. So our model was significantly more predictive than the simpler model. But our R-squared value was just 0.31. That is to say, our model only explained 31% of the variance. And that's not a lot. That's not even half the variance. So maybe if we add more predictors, or if we add better predictors, we could actually explain more of this variance. We could make more accurate predictions. But how might we improve the model? Well, like I said, we can try adding more predictors. Maybe we observed there's some individual differences between our participants that might be related to the amount that they're tweeting. So maybe we found that older participants don't tweet so much, or that they had very low posting anxiety. Or maybe we found that our youngest participants were our most prolific tweeters, that independent of their posting anxiety, they were just tweeting up a storm. An observation like this, either from looking at our data or from reading related literature on the topic, might inspire a new research question. It might inspire a new hypothesis about how age could also be used in our model for predicting tweets. So last time, a couple weeks ago now, we built a model that says that you can use social media posting anxiety to predict tweets. But now we want to build a more complex model in the hope that it's a better model for predicting tweets by adding a new variable. That variable will be age. So now we have a new hypothesis. Not only will social media posting anxiety predict the amount of tweets someone makes, but age and anxiety together will significantly predict the number of tweets. As usual, we want to formulate this hypothesis in a scientific way. We want some understanding of what the null hypothesis is that we're trying to falsify. Just like last time when our keyword was predict, that was letting us know we had a regression model. Once again, we are looking out for that keyword predict. This time, because we have more than one variable predicting the value of another variable, we know that it's multiple regression rather than simple regression. But yeah, once again, that keyword is predict. And I also made the word and big because we're using multiple variables to help us make that prediction. So that's how you know you're using a multiple regression. And likewise, if you have a hypothesis like this, you should know you're using multiple regression. If you're using multiple regression, you should know that you're testing a hypothesis that makes predictions. So again, let's flash back to last week, and hopefully this isn't just us flashing back to last week, or hopefully you have a good memory of our last lecture if we're flashing back this much. But last time we had the equation of a straight line. To make our prediction, all we needed was the slope of the line and the point where that line intersected the y-axis. We used that slope and that intercept, that straight line equation, and we could make a prediction about where our outcome variable would be. Then we could use our actual observation to get a residual value. So we would know not just where our prediction was for that given point, but we would also know how far above or below a given point was by making an observation. This is going to be just the same this time, but it's going to look a whole lot more complicated. So brace yourselves. If you've already started reading the second half of chapter 7, you've already seen this diagram, but this looks, manageable. This looks like, oh yeah, that's just a line in two-dimensional space. That's easy. This will look tougher than it really is. This is a 3D visualization of what multiple regression is. So it's multiple linear regression. That means we're drawing multiple linears, multiple lines, I should say. And that means instead of making a single line that best fits our data, a regression line, we're actually making a regression plane in 3D space. So we're making a flat surface, a 2D surface that uses two variables to predict a third variable. If we were using more than 2 predictor variables, it gets a little harder to visualize. Now we're talking about 4-dimensional space, but in any case, we're always just making a surface or a 2-dimensional, in this case, a flat 2-dimensional surface that has 2 slopes, or a surface with the number of slopes that you have predictor models. So finding the equation of this surface that has the same number of dimensions as our predictor variable is just the same as finding the slope of, finding the equation of the line that has just 1 predictor variable. This image on the right comes from our textbook. The authors wondered if we could use both the number of times an album was played on BBC Radio 1 and the amount of money spent advertising a song or an album to predict the total sales of that album. And this really doesn't look that different from simple linear regression. We've just added 1 additional predictor variable. That means we have, instead of just 1 line, we have a second line, and that line also has a slope. The equation is still just the same. Each predictor variable gets a value multiplied. Each predictor variable value gets multiplied by its slope. And then we add in the intercept value, so the intercept for the entire axis rather than for a single point on that axis. And then we have our prediction. And from that prediction, we can see just how far away our actual value was from the prediction, and thus we get a residual. So this just keeps on adding. If you had 5 predictors, it would be beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3, on and on and on. You just keep adding as many betas and as many x's, or as many predictor variables as you need. But there's no limit to this. You can have as many predictor variables as your heart desires. And all you also need to add on at the end is an intercept and a regression term, a constant term. And those slopes and those values help you make your prediction, your y, your outcome variable. So you can pretty easily imagine how this equation can grow and change as you get these more predictors. This week, we're just going to talk about adding 1, but it's just the same if we were adding many predictors. There's no limit to how many predictors you can add. That said, you might start getting diminishing returns, that your predictors will probably be less and less theoretically related to your outcome variable. That if we were just trying to predict the number of tweets someone made, sure, we could add in things like people's shoe size or their zodiac sign or the number of sandwiches they've eaten in the last month. But as you can imagine, these probably wouldn't have strong theoretical ties to the number of tweets they make. They probably would not add much to our model. That's why, just like with simple linear regression, as we build this model, as we make it more and more complex, we have to compare how good it was to a simpler model. Last time, we only had 1 model that we were comparing to. We were just comparing our regression model to our mean. But for multiple regression, depending on how we build our model, we can compare that model to any number of smaller, more simple models that we could have used instead. So how do we assess how good of a model we made? What do we do to assess the value of our model? Well, this starts out the exact same way that simple linear regression started out. We use the method of least squares to calculate our total sum of squares, our model sum of squares, and our residual sum of squares. And we use those to obtain our R-squared value. And this is just the same equation that we covered last time. It's just comparing your model sum of squares to your total sum of squares. Sorry, comparing your residual sum of squares to your model sum of squares, and then comparing that to your total sum of squares to get a R-squared value. This value is called multiple R-squared this time, instead of being the coefficient of determination. It's just multiple R-squared because it accounts for multiple different sources of residuals. And this multiple R-squared value, once again, lets us put a single number on how much variance was explained by the model. So with simple linear regression, we saw that the R-squared value was the exact same as the square of R being the correlation between our predictor variable and our outcome variable. This time it's almost the same. This time we have multiple predictors. So R-squared represents the square of the correlation between our prediction, our overall prediction for a given point, and the observed values for that given point. So after we've used our regression equation to make a prediction, we get our prediction values. Then we can also check what our actual observation was for all of those points. And we can see how closely related our predictions were to the outcome's actual value. And that's exactly what R squared is telling us. How closely related was our model's prediction to the actual outcome for the variable we were trying to predict. So how do we build the model? How do we choose predictors and how do we fit them into a regression model? The way I put this is that there's two approaches to building a model. There's the big data approach where you just throw everything at the wall and see what sticks. And then there's the theoretically driven approach or the scientific approach in which you build a model based on previous work, based on theory, understanding of the concept that you're trying to model, based on maybe experiments that you're running or observations that you're making. The big data approach has some downsides. It can be costly to collect lots and lots of data. It can be invasive to collect lots and lots of data. Even if you already have your participants' shoe size and their zodiac sign and the amount of hours they spent in the last 3 months watching Korean dramas on Netflix, you don't really, do you really want to have to collect that data every time you're going to make a prediction about how much they're going to tweet? You might have all of that stuff for one set of participants. But if you decide that that's your best model for tweets, then every time you want to make a prediction, you're going to have to collect all of that data for all of the rest of your participants as well. As an aside, even if that model helps you increase your R squared value and explain more of the variance of your data, it might not help that much. It might just make these tiny incremental improvements to your prediction. It might make them just a tiny, tiny bit better at some cost, at some high cost, possibly, if these are expensive variables to get your hands on. Theoretical models also have the black box problem. If you don't know why you're putting something into the model, if you don't know why you're adding a variable, then you won't have much ability to explain why it helped with your predictions. The scientific approach, on the other hand, a model that is built theoretically, comes with explainability as a feature. If you had a strong theoretical reason with lots of research supporting why each different predictor was added to your model, that gives you a much better footing for understanding the underlying phenomenon that you're measuring and for explaining how your model works instead of at the end being like, really sure why shoe size helped us predict tweeting. You would be able to say something like age helped us predict the number of tweets, and this was because we observed a correlation between age and tweets. Someone asked me in a DM, do we control these variables or are they just random? In this case, we're talking about variables that we're directly measuring and using to predict some other variables. So these are all, I wouldn't call them random, but I would call them observed rather than controlled. I'm not assigning anyone an age or a shoe size or an anxiety score. I'm observing all of those things about somebody and using those to predict their number of tweets. And this is still very much in the camp of cross-sectional work. So the same sorts of studies we use for correlational studies and for simple linear regression studies are the same here, that we're not designing an experiment, we're observing these variables, or we're asking people to tell us what their values for these variables were. We're not manipulating them ourselves. There's no independent variable and there's no dependent variable. So this is how we choose what predictors we might include. In this class, we definitely, or your entire degree, we will definitely hope that any variable that you add to a model, you have a good theoretical reason for adding that to your model. But that's not to say that that's the only sort of model you'll ever encounter. So even though I don't necessarily support throwing everything you have into the model and seeing what comes out, I still teach it because inevitably you will see models like this, particularly if you end up working in big data, in machine learning, for instance. They sometimes use the more exploratory, throw it at the wall, see what happens kinds of models. So the order in which we add our variables helps determine what we can say about our model. So it's not just that we have this collection of variables, but we have to determine what we're going to compare our model against. If we're building a model theoretically, we want to compare our new model to some known model. We might, in this case, use what's called a hierarchical entry method. So in our Twitter example, our past work showed that anxiety predicts the amount that people will tweet. So we'll start with a simple model that's just using anxiety to predict number of tweets. And then we'll compare that, we'll add to that model age as a second predictor value. And now we'll be able to compare our new model to an established model. So instead of just comparing our regression model to the mean, if we build our model hierarchically, if we say, here's the mean, here's our simple model, here's our new complex model, and that simple model being something that was previously demonstrated in literature, now we can make more specific claims about what our new model helps with, that we can say not only is our new model better than the mean, but it's actually better than existing models. If on the other hand, if we want to explore some new area that we don't have any strong ideas about what predictors might be better or worse, but we have a bunch of variables, we have a bunch of predictors, and we want to compare just our bag of many predictors to the mean, we can do that. This is called forced entry. This is where you just shove everything into the model and then compare that to just the mean alone with no simpler model. This is okay. This is how models tend to be built using kind of that big data approach that I keep mentioning, that you're just comparing all of your predictors together against the mean. You can't really make comparisons between predictors. These aren't meaningful comparisons the way it would be more meaningful to compare hierarchical models, to compare one predictor to the more complex model with multiple predictors, but you still can compare against the mean. So you can still say something about whether your model was predictive in aggregate. Someone said, for example, 94% of the emails sent around the world are spam. If we can create a model that says that all the emails are spam, then our model is 94% correct, but that isn't a good model. Yeah, that's a good way of putting it, that you have you have two kind of risks with a model. There's like overfitting and there's underfitting. That a model that says that only uses whether a message is email to determine whether it's spam, and says that if a message is an email message, then it's spam. That might successfully detect a lot of emails, but it's probably not a good model, and it's probably worth getting even a little more, even increasing your R squared by just a little bit, so it doesn't flag absolutely everything as spam, right? That you want, in that case, just because you have a 94% fit, you would still need a slightly better model. On the other hand, for like maybe a less applied or a we'll say for a less applied idea, like predicting the number of tweets someone has or someone will make, then maybe 34% or 31% or whatever predictive power, maybe an R squared value of 0.31 is fine, that you're not really aspiring for 94% as long as you can kind of get close. So yeah, I think that's a good example of how the raw predictive power of your model, the raw R squared value, doesn't necessarily tell you how good or bad a model is for its purpose, because yeah, some models need to be very, very precise, or others need to be less precise, or anything better than 0 is helpful. So these are two options for building your model: either build it up from a smaller, simpler model, and then a more complex model that adds something to that model. That's the hierarchical approach. The forced entry approach, just take all the variables you have, put them all in the model to start with, and then only compare that to the mean. Those are both perfectly fine, valid ways to build a model. Here is a bad way to build a model, the stepwise approach. Don't do this. This method's died out a little bit. This was kind of popular in the 90s and 2000s because it was like new computer technology we had, that instead of just doing the forced entry method, what if we let the computer do it for us, man? Instead of coming up with a theory, we could let the computer look at our model, see what was the most predictive, and then build those smaller, simpler models from that. And then it's like cheating on the test, right? It's like peeking forward when the teacher asks you a question and then acting like you knew that all along. That's what stepwise model building does. It starts with that forced entry regression. It puts everything into the model. Then it goes back and tries out different hierarchical models based on the order that it found in the forced entry method. So it can either just add one variable at a time and compare them all against each other, or it can go backwards. It can start with everything and take one away at a time, or it can do both. It can do the what do they call that? The both approach. Field describes it in the book. But It can be forward, backward, or both in terms of building these like simpler models that are not theoretically driven. And now the data analyst can claim that they can compare their complex model to these simpler models. And they can claim to compare that their model was better than those simpler models. But there's a major flaw in this approach, and that is that it's an atheoretical approach. That it seems like it's a great way to compare your model to simpler models. But because it's atheoretical, because there's so much random noise in your collection of variables, it turns out that models built this way and compared to these simpler models don't replicate. That if you get a bunch of new data and then try to compare those same complex models to those same simpler models, they just don't have the same comparisons as what you observed the first time around. That all the random noise you observed the first time influences your decision of what to add or what to take out of that complex model. And you make these predictions that end up being completely wrong. So for that reason, we don't use the stepwise approach anymore. Again, this is this idea of like peeking, looking ahead on the homework. It's getting your forced entry, throwing all of your predictors in there, and then taking one away, taking another one away, and then comparing your big everything model to the one where you took a few away and saying, like, look how much better my model is than this simpler model. And the reason we don't do that is because those simpler models just don't have any basis in predicting anything. They don't replicate as we get more data. It just introduces a lot of random noise. So that's one we don't really do anymore, but you might see models like this, and the book talks about it. So I wanted to mention the stepwise approach. Finally, this one's better than stepwise. It's not used so frequently, but it's becoming a bit more popular. It takes a lot of computer power to do this sort of modeling, but now that computers are a lot stronger than they ever used to be, you will see them now and again. This is called the all subsets approach. So instead of peeking ahead and trying to find those simpler models that your complex model can beat, the all subsets approach tries every single possible combination of predictors and compares all of those different models against each other. So if you had just anxiety and age, there's just 4 subsets. It would be using anxiety to predict tweets, age to predict tweets, using both to predict tweets, and just using the mean. So that's for 2 predictors, that's 4 models. That's not so bad, but that means if you have 10 predictors, that's 1,024 possible models that all need to be compared against each other to find the most predicted model. So you can imagine how long that could take for R or for whatever statistical program you're using to run to compare all those models. This very well might help you find the best combination of variables, and you'll probably get a lot less false negatives. You'll get a lot less non-replicable models or results than you would with the stepwise approach. But it still doesn't mean you have a good understanding of the phenomenon if you use the all subsets method. If you include like 80 variables and you find that these 7 all help predict tweets, you don't really have a good handle on why those 7 were predictive or why any particular other variable that you didn't include wasn't predictive. You're still just, you might use this to explore relationships without a hypothesis if there's just not a lot of work on the field that you're looking into. This might be an appropriate tool in that case, but it's not very theory driven. So it won't really help you test a hypothesis. It won't help you discuss the implications of your results. It more just helps you maybe get an idea of what sort of research you should run going forward, what sorts of experiments or future correlational studies you might want to look into. So if you're doing exploratory work, an all subsets model where you compare every combination of variables, that's okay. A forced entry model where you compare all predictors against just the mean, that's okay. Or if you're doing more confirmatory work, if you have theoretical reasons to think that adding a particular predictor will make your model better, then you want to stick with a hierarchical model. You want to take your mean and take your simpler regression model, and then you have your new more complex model, and then you can compare your more complex model against both your simple model and your mean. So in the example we're doing this week, we're saying that last week's or last class's model where you use just anxiety to predict tweets, we're saying that that's now like a confirmed in the literature good model, a good simple model that we can compare a more complex model against. we're taking a theoretical approach. We're going to use a hierarchical entry method. So we're going to compare our new age plus anxiety predicts tweets model against our model where just anxiety predicts tweets. So yeah, how do you choose between these entry methods? I guess I didn't remember that I wrote this slide up, but it's going to be just the same. If you have a previous model that you're building upon, go for a hierarchical model. If you're building a model, think about what your research questions are. If you're testing a confirmatory hypothesis like we are, we're testing this idea that that age can predict tweets, or age and anxiety together can predict tweets, and we're trying to test that against the idea that just anxiety can predict tweets. In this case, we have a specific prediction we're making. We can compare it against a specific different model. If on the other hand, you're not sure which, if any of your predictors are any good in predicting your outcome variable, then forced entry or all subsets can be appropriate to do that exploratory work to get a better understanding of your variables. From there, you can kind of build up more theoretical design by having other studies that test one variable at a time, or that start to look into some building experiments to test causal relationships between variables, things like that. That way you can eventually build these nice hierarchical models. Throwing stuff at the wall and seeing what sticks only leads you to having a messy, sticky wall is the way I think about that. So that's how we decide about how we add our predictors, which predictors to add. But how do we know what predictors are even appropriate to add? What are our assumptions for predictor variables? So just like with simple linear regression, our predictor variables must be either continuous or categorical. So either they have a number associated with them or that they have a category. So you can use categorical variables. You could use, zodiac sign, for instance, as a predictor. We also have the same assumptions as last time, that there's a relationship between the predictor and the outcome variable that is linear. So each observation, that there's a linear relationship, and rather than some other relationship that if you know there's like a parabolic relationship between your predictor and the outcome variable, then it's not really appropriate to include, because you're just drawing lines in regression. Likewise, each observation for the outcome variable has to be independent. They have to come from a different person, for instance. You must also, for your predictor, have more than 0 variance. You must have some variance. What do I mean by that? So let's think about our tweets example. Let's say we want to include age, but all of our participants were exactly 32 years old. In that case, we could not add age as a predictor variable because there's no variance, because everyone had the same age. There's no new information that age can give us as compared to the model that doesn't include age at all, because everyone has the same reading for that variable. If, on the other hand, we had at least one person with a different age, then we could include it. So as long as you have any little bit of variance for a predictor, that's fine. You just can't have a predictor where everyone had the same exact value. Next, we cannot have perfect multi-collinearity. That is to say, we can't use a predictor variable which is perfectly correlated with another predictor variable. And this is the same problem as the age thing. If we used age, we can't really use, say, year of birth as a different variable, because your age and your year of birth would correlate perfectly, that as one increases, the other one increases. Likewise, we couldn't use like age since turning 18. You can't just keep adding the same variable with different names, as there isn't any additional information you're getting out of that variable. If two variables perfectly correlate, if they perfectly rise and fall together, they give no additional information beyond a model that just didn't include one of those variables at all. The book suggests that any correlation stronger than 0.8 between any of your predictors is too strong, and gives some methods for checking this. I mentioned in the announcement this week, the R script that we're going to look at in the second half of class has some bonus information at the bottom about how you can check this multi-collinearity all in one step, but you can also just run a bunch of correlation tests between your predictor variables just to make sure that there's no predictors that are perfectly correlated, that are multi-collinear. Finally, our last assumption is that the final residuals for our model, the predictions we make at the end, how far they all are from our observed variable, we have the assumption that these residuals are normally distributed, that they're patternless, that they're centered around 0, that it's not like our model is guessing too low for everyone, or it's guessing way too low for some people and way too high for the others. Instead, we want a normally distributed, centered around 0 set of residuals. This isn't to say that we need each of our predictor variables to be normally distributed. We can actually use predictor variables that are not normally distributed, but it's a bad model overall. We can't use regression if we find at the end that our residuals, that our predictions were not normally distributed. And again, in the R file at the very end, there are these extra tests that you can use to look at your residuals. If I'm being honest, this is a little bit technical. We don't use it as a core part of this course. It won't be tested in any assessment. It won't be part of either written assignment or the multiple choice tests. So don't worry, I won't ask you to look at the patterns of residuals from a multiple regression, but this is just another assumption that I wanted to make sure I told you so you know everything there is to know about multiple regression. But yeah, that's the only assumption of normality we have here, just that our residuals are normal, not that any given predictor variable is normal. And how many participants do we need for our regression? So this depends on how many predictors we have and how much statistical power we need. You probably read a little bit about statistical power in the first couple chapters of the book, but they give some rules of thumb for multiple regression that some sources say about around 10 participants per predictor variable, others say around 15 participants per predictor variable as a minimum. But the minimum really depends on how strong the effect size is. How much does each predictor actually impact your outcome variable? The smaller the effect, the less a predictor influences that outcome variable, the more participants you need to confidently differentiate that effect from 0. If you get into more advanced statistical analysis, you might look into estimating how large of a sample you need using a power analysis. But in general, for this class and in general for your thesis, if you're doing a thesis in ICS, the bigger the sample you have, the better. The more predictive your regression will be, the better it will be at differentiating effects from 0. Failure to support your research hypothesis does not necessarily prove that your null hypothesis is true. You might instead fail to detect an effect because you might, on the one hand, fail to detect an effect because there is no effect, because the null hypothesis is true. But on the other hand, you might fail to detect an effect because you just didn't have enough statistical power to detect it. You just didn't have enough participants. And that's why we just say the more participants, the better, because the more you have, the more statistical power you have. And that means the lower the chance is that you failed to detect an effect that really was there. So the more, the better. But as long as you have at least 15 participants or so per predictor variable, you should be all good. When we do predict an effect, we can reject the null. Yeah, that's right. If you find a significant effect, then that's when you can reject the null hypothesis. But when you don't find a significant effect, that doesn't mean that your null hypothesis was true. That means you're left in this point where you're like, if I only had recruited more participants, would I have found an effect? Or was there no effect there at all? That's where you get existential about research, at least if you are me. So that is how you set up a multiple regression model. Now let's look at what it looks like in R. So this is what it looks like when we use a multiple regression. I have a data set called twitter.mult, so Twitter multiple regression, tweets as my outcome variable, and with anxiety and age as my predictor variables. And we get the same sort of output that we saw last class. So it looks just like our simple linear regression output. And it's even the same equations or the same formulas in R to make all this happen. Those same important spots that we looked at last time are just what we're going to be keeping an eye on this time. One big difference is that this time our output does not do everything for us. It doesn't know whether we were using a forced entry or a stepwise or a hierarchical model. It doesn't give us all of the information we need. It tells us what our R squared value was. It tells us how much better our model was than the mean, in other words, but it doesn't do that intermediate step of comparing our model to simpler models. So if we are using a hierarchical model, we have to do that as kind of a step 2. We also have the problem that these slopes are kind of hard to compare to each other. These betas are hard to compare because these predictors have different units. That anxiety score was, it was on this like scale from like 20 to 80, which is pretty similar to what age is on a scale of, but they are different units. That we might have had a participant who was 18 or a participant who was 91. These values would not have been observable in the anxiety variable. This would be even more apparent if we were using something like shoe size, like where shoe sizes might be on a scale from, I don't know, let's say 25 to 48 or 50, 58. I don't know European shoe sizes. I was born in America. I only know my own shoe size. But in this case, we would have a very different scale for our variable. So the slope not only reflects how predictive that variable was, but it also predicts how different the scale was compared to our outcome variable. So when we just compare these estimates for the slope, that doesn't really tell us which was doing more of the heavy lifting because they might just be in different units. They might have had to be transformed in different ways to make that prediction. That means that one of our other steps we need to take after this outcome is to get a standardized beta, is to get a slope that is in the same unit for all of our predictors. That way we can make those direct comparisons between our predictor variables. So this is kind of step one of our multiple regression output, where we get our unstandardized betas. We see our p-values for each beta. We see our squared value and our F statistic, which just is comparing our whole model against the mean. But we still need to compare our complex model against our simpler regression model. And we still need to get standardized units for our slopes, for our betas, so we can compare them to each other. So here is some more R output, and this is just two really simple steps that you can take after you do your main regression step. So after you get your R squared value and you see if you have a predictive model, you also can now compare your model to the simpler model. So I put in two models into ANOVA. That's a command that just analyzes variance, and in this case, it runs an F test. You can see that F there. And now instead of comparing our multiple model to the mean, it's comparing our multiple model to our simple model with just anxiety. So you can see model 1 was using just anxiety to predict number of tweets. Model 2 is using anxiety and age to predict number of tweets. And again, we get an F squared test, F value, and we get a P value for that F squared test. And in this case, we can see that our second model, our anxiety and age model, was not significantly more predictive than our anxiety model alone. That our more complex model was not significantly better than our simple model that just used anxiety. And that isn't too surprising when we remember, if we look back one, that age was not a significant predictor on its own, that age was not significant. So adding age to the model with anxiety did not improve the model for predicting tweets. Underneath that, we have our standardized beta. So that's just using one really quick little command in R called lm beta. And that gives you your slopes or your betas in units of standard deviation. So these will be all between -1 and 1. And this lets us compare our betas, compare our predictors against each other in the same unit. Standardized betas, instead of asking for every increase in anxiety score by 1 point, how many additional tweets did you predict? This is saying for every increase in anxiety score by 1 standard deviation, how many additional standard deviations of tweets did we predict? That means every unit for every single beta is exactly the same. We can weigh up their relative importance to each other just by comparing their standardized betas. In this case, we see a pretty big standardized beta, pretty different than 0 standardized beta for anxiety, and a much smaller one for age. And as we already know, age did not even have a significant p-value. So we already knew that anxiety was doing more of the heavy lifting than age, but now we can compare them straight up and say that, yeah, this was a much more important beta, a much more important variable for us than was that. And this is actually what we'll want to report when we report a regression, that rather than telling people those unstandardized units that are hard to compare against each other, we'll make a table that includes their standardized betas, the standardized slopes for each predictor model. That way, at a glance, a reader can compare the relative importance of each predictor variable. And It's that funky slide that everyone loves that we throw at the end, how to report this test or how to report this analysis. So just like we did with simple linear regression, we're going to want to use a table and some words. It's extremely important to use a table now because the more predictors we get, the longer this table becomes, the more betas we'll need to report, and the more t-scores for that beta and the more p-values. Those t-scores just come from the output for the first regression. So that's the t-value right here. The p-values come from that first output. And those standardized betas just come from that lm beta command that we ran. So this is just the transforming the beta that we observed. So the numbers that are up here in our model, transforming those into standard deviation units instead of their original unit. So this would be like ages per, or this would be like tweets per year alive, and this would be tweets per anxiety. In this case, these are just nameless, unitless standard deviation units. So this is just a number between 1 and 1. And we can report this in words. We can say that for our hypothesis, we could say that we found our participants' level of anxiety predicted their number of tweets over the past 6 months. R squared equals 0.32, F of 2 and 97 equals 24.1, P is less than 0.001. And that's from the F test for just our basic regression, or for our regression model compared against our mean. But we also have that F test of our models compared against each other. We report that next. We'd say this model was not significantly different, however, from a model that uses anxiety alone. F of 1 and 97 equals 2.66, P is 0.106. And then we would say that the full model equation and the betas are reported in table 1. And this is where we might say that our hypothesis received mixed support, that our model was better than the mean, or we might say that our hypothesis was rejected if we thought that this model was going to be better than our basic model. So depending on what your hypothesis is, this might cause you to say your hypothesis received mixed support or that it is rejected. I think the way I originally phrased it was just that these two variables can predict number of tweets. In this case, we would say it did receive mixed support. They did predict the number of tweets. They just didn't do it any better than a simpler model that only included anxiety. If a variable isn't significant, should you still include it in an ANOVA? Yeah, so if, so to be clear, I want to shy away from calling this an ANOVA because in a couple of weeks we will learn ANOVAs. Even though this uses ANOVA as its command, this is an F squared test. You should still include it if you're making a hierarchical regression. So if you want to say, if you want to assess whether your complex model was better than the simpler model, you should include that, because if we only looked at this, we're only comparing our complex model against the mean, we would say, actually, yeah, this model is significant. We should keep it. On the other hand, since we knew that this was a simpler model we could compare against, we wanted to compare these against each other using this F squared test. And what we found, or using this F test, and what we found was that, no, they were not significantly different. So we do still want to include it in this F test and the command afterwards if we're doing a hierarchical entry method, if we're comparing against a simpler regression model. If, on the other hand, we're just exploring our data and didn't have a specific model to compare against, we might run, we might run this and find, oh yeah, age was no good. Let's try every other combination of, let's try all subsets, right? Let's try every combination of models and see which one is the most predictive. In that case, then maybe we wouldn't end up including our insignificant predictor at the end. We would say the most predictive model among all of the subsets that we tested was the one that just uses anxiety. That would be fine. That answers a different research question than the one that we were trying to answer here. Since we were using a hierarchical entry method, since we were comparing models against each other, we would want to include that insignificant value because we would want to say, or that insignificant predictor, because we want to be able to say this at the end. We want to say that our model was not significantly different than the simpler model. Someone asked, what is a t-score? That is getting back to this idea of using a test statistic with a known distribution, that we are comparing whether or not this predictor was significantly different from 0 in terms of making a prediction. So was this predictor, did this predictor help us make a prediction? Our null hypothesis is that it did not, that it was no better than 0, that the difference between this model and the mean model is nothing. So a high t-score, a t-score very different than 0, either very negative or very positive, is on this known distribution, this t distribution that you might have seen in the textbook. And if it's very far from 0, that's how we assess our p-value, that we now know, okay, this was, because it's a known distribution, we know that there was only in this case, a 4 times 10 to the negative 10th chance of observing this, given the null hypothesis due to chance. So we know that this prediction, this particular predictor variable was significantly predicting our outcome variable. On the other hand, this t-value is pretty small. It was pretty close to 0. So we're saying there was a 10% chance of observing this, given the null hypothesis due to chance, that it was a little better than the mean, but not much better. So that's why we have a relatively high p-value and a relatively small t-value, that t-score is not that different from 0, because on this distribution, the difference between having this variable or not having it was pretty close to 0. So we're not rejecting the null hypothesis for that variable. We're not rejecting the idea that this was no different than 0, than not having it. But you can read a clearer explanation of t-scores and test statistic distributions in the textbook. Andy Field does a better job of it than me. No, the ANOVA command in R is not actually a t-test. Everything's very confusing because ANOVA just means analysis of variance. That's just a shortened phrase, but the ANOVA command can run any number of different test statistics. So in this case, it was running an f-test. In future weeks, it'll be running, it might be running a t-test if it's comparing multiple means. But ANOVA is just a catch-all that means analysis of variance. So in a couple of weeks, we'll talk about an ANOVA test, which is an omnibus test that compares multiple means. In this case, you are analyzing variance between 2 models, so you use an f-test. In either case, they are comparing against some test statistic distribution, whether it's the f distribution or the t distribution. There is no ANOVA distribution, but this ANOVA command hides a lot of different sorts of tests inside of it. Anyway, you can learn more about multiple regression by reading the second half of Chapter 7, Discovering Statistics Using R, Chapter 7, Regression. The second half of the chapter has a lot of information about those assumptions tests that I mentioned, like multiple collinearity and normally distributed residuals. After you get a handle on all of those things that you would want to check and how Andy Field checks them, you can check out the second half of the R script from this week, where I have some of the code for doing that. That way, if you run a regression in your own life outside of this class that has multiple variables, then you can go ahead and run all of those assumptions tests. So hopefully, yeah, you can check that out and return to the R script just to make sure you have a handle on it. Or if anything in the second half of the R script that we don't cover today is confusing to you when you check it out later on, just email us. I'm happy to answer some questions about it. I kind of crammed it all in together because Andy Field does all of the explaining for me. But if anything's unclear in that script, please do let us know. And speaking of letting us know, between now and our next class in 2 weeks, I would really appreciate if you could fill out a feedback form. So this is an anonymous Google form. I'm not asking for your name or your email. I ask what degree course you're in, just to kind of know whether you're one of our ICS MSc students, or if you're doing a PhD in some other department or whatever else. You don't even need to answer that. You can just say prefer not to say if you really don't want to be identified. But I just have a couple of questions about what we're doing well and what we could improve on. That way, for the last couple lectures after the reading week, we can try to improve QDA, make it even better for you in time for the second assessment and in time for the final assignment or the final quiz. So if you have a chance to fill this out over the next couple of weeks, please do. Please take some time with it. Give me some thoughtful feedback, even if it's just to say, you know, this class is horrible and here's all the reasons why. You can totally tell me that. As long as you answer kind of honestly and thoughtfully, that helps me. It helps me become a better teacher. So yeah, you can use the QR code or the link, or you can type it out like a caveman. But any feedback you can give us would be much appreciated. Anyway, it is 2:55 now. I was waiting for the clock to roll over. It's 5 minutes to 3. why don't we come back together at 5 minutes past 3 and look at the R script this week. And you can leave any questions and comments in the chat. I'm happy to answer them either during the break or when we get back. See you. All right, hello, welcome back. I am seeing relatively few questions and comments in the chat, which either tell me that I am becoming the world's greatest stats teacher, or I have a lot of feedback coming in the form of emails and feedback form comments in the next couple of days. So I look forward to your emails all weekend long, as much as I always look forward to them. But hopefully things are going pretty smoothly. And this is kind of the part, the time of the year in this class that people do sometimes start to hit their groove, that they're getting more comfortable with R and getting more comfortable with statistical concepts. And we find that by no coincidence, it really does coincide with when your first assignment is due, that when you have to put in all the work to get an assignment together, then suddenly you're like, oh, that's how you do this. And oh, that's why this happens this way. So hopefully you're having that experience, but if you're not, do reach out to us. We're here to help. So let's get things started with week 7.R, which I struggled to not call like lecture 6.R or something like that. Discussion. Yeah, that's grand. However you want to submit is great. This is actually a great time to say this because people are probably listening. You can submit everything in one Word document. You can submit everything as a bunch of different documents. You can submit a PDF or a Word document of your text, and then a .r file of your R code. Any of these are fine. The only thing I really ask that you don't do, and I mentioned this before also, but please don't submit zip files or .7z files or whatever. Don't submit compressed folders to me. Because then that means I have to play is this malware roulette, where I have to download a file that you uploaded to Brightspace, and I have to hope that it doesn't turn my computer into an expensive paperweight. And I've played this game for a couple of years and I've never lost yet, but I don't want to start risking it now. So no compressed files, please just send me files that I know exactly what they are when I look into them. Also, if they're PDF or Word files, I can open them right in Brightspace and read them right there in my browser and not have to download them. But anyway, that's enough about file types. Let's get back to R, week 7, the thing at hand. So as always, we will start by setting our working directory, and we can load in our new data set. So I have the little joke here that you can call it anything you want. You can call it twitter.molt is what I called it, but you can call it tweet anxiety age, data 2. I hate calling things data or data 2 because then you don't remember what is even in that data set. I like actually naming my data frames something informative. So molt here for multiple regression. But you can call it anything. That .molt isn't magical. It doesn't do anything special. You can call it Justin is great. Love that. So I called it twitter.molt, and I get 100 observations of 5 variables. I think I need to update my R. Is why things are getting weird for me. In my case, I'm seeing when I run the head and the tail of this data set, I see 5 columns. Now I have the X and ID. I don't really want X at all. I don't really want ID either. So since I know this is cross-sectional work, I don't need that ID column because I know every different row is a different participant. So I'm going to make X equal to null. I'm actually also going to copy this and get rid of my ID column because I know I don't really need that this week either. So I'm going to call ID equals null. Now if I run head and tail again, it should look a lot cleaner. Yeah, now I just have 3 columns and, oh geez. The Windows narrator started talking to me. That was weird. I must have hit some secret key command to start accessibility features because the Windows narrator started reading my RStudio to me. I'm glad you couldn't hear that. It was traumatic. So now we have just 3 columns, just tweets, anxiety, and age, and that's all we're going to need for our regression models. And we're just modeling exactly what our hypothesis was in class today. So we're going to see if we can use anxiety and age to predict tweets, and we're going to see if that model is any better than the model we came up with last week, where just anxiety alone can be used to predict tweets. You can see that I generated this data randomly and without too much thought, judging by the fact that anxiety scores are going to like 7 decimal places when actually these should have just been whole numbers. I remembered that ages are whole numbers. Sorry about sloppiness in that regard, but it doesn't matter. And it's actually fine that it's showing that, because now you can use a whole number as a predictor. You can use a number with many decimal places as a predictor. You could use a category if you had one, but no, we're just going to be using these 2 predictors to predict number of tweets. And we, as always, will start with our descriptive statistics. And this week I put them all on one line in case you want to do it that way to make your life a little bit quicker. So for tweets, there is our mean, our standard deviation, our min, and our max. For anxiety, we get the same thing. And for age, we get the same thing. And maybe you would want to include median or interquartile range in there. We know we have 100 participants, so we would probably say n equals 100 somewhere in our results section or something like that. But in any case, we get whatever descriptives that we're interested in keeping, and we can make our visualizations. And remember, as we talked about, we're just using these visualizations to check for bad data points, to check for like extreme outliers or impossible values. We are not worried about a normal distribution with regression. We can actually use non-normally distributed predictor variables. We could use predictor variables where everyone had the same exact age except one person was older. And that wouldn't be a normal distribution, but it would still be a perfectly valid predictor variable. So we're not so concerned with the distribution. We're just looking for weird data points. So let's look at our box plot of age. And I picked a y-axis limit from 0 to 80. You can see I'm starting to include some different things into the code just so you can kind of get a better handle for all the different ways you can essentially modify different commands that we're using all the time. So I included the y limit for box plot between 0 and 80. And it looks like there aren't any weird scores. It looks like my lowest age was around 20. My oldest participant was maybe in their mid-50s. So nothing out of the ordinary there. No one that was way older or younger than our sample, and no one who was some impossible score. I didn't have like a negative aged person. So that looks fine to me. I'll also just make a histogram to see if there was anyone like way off on their own somewhere, but no, it looks like everyone was kind of bunched in this like 20 to 60 age range, and that's great. So we won't have to do anything with the age column. Let's also look at our tweets column, just like last week. And we already kind of know from last week that this one potentially high value for tweets that the box plot is identifying as a potential outlier. We checked last week and we found that it wasn't an outlier, but we will check that again. But just to note, yeah, it looks like we have maybe one potential outlier and no impossible values, nothing that's like below 0, no one that had like 6 billion tweets. I guess that's not impossible. Elon's probably in that range, but no normal person would have been in that range, and we didn't find anyone like up in the billions. So we're all good with the values of tweets. And we'll look at the histogram. And again, just looking for weird data points, but it looks like everyone's kind of bunched in that 0 to 500 tweets. And again, we're kind of imagining this as like tweets in the last 6 months. I don't know how often like a person who tweets regularly tweets. Do you tweet 100 times in a month? That's probably too much. I don't know. 3 tweets a day? I could see it. So that's our histogram and our box plot for tweets. And we'll also check anxiety scores. And remember, anxiety scores was on this was on a scale from 20 to 80, and it looks like everyone is in that range as well. No one was over 80. We already checked, by the way, that our max was under 80, and it was, that our min was over 20, it was. So we already know there's no impossible values for this scale, and we don't see any potential outliers either. And we'll do a histogram, and this time I put the sequence thing instead of break. So seq 0, 100, 10 is the same as 0, 10, 20, 30, 40, 50, 60, 70, 80. It's this, I just put it that way so you could see here's a quicker way of doing it in case you're getting tired of writing out all of those sequences every time you make a histogram. But again, we see that we don't have any strange or impossible values for anxiety score, so we should be all good to go here. Let's just check that potential outlier on tweets. So again, if we looked at the box plot, we saw this one potentially high value. Let's see what that value is. And we can do it this way. So last week we did it one way where it was like which this is this. This time we're doing it this way. Twitter.molt. So from this whole data set, we want every point in that data set where tweets is greater than 500. And that's the row. And then we want every column. So comma and then nothing after the comma. So we want any row where tweets was greater than 500. And we want all of the columns in that row. That's what this syntax means. From this data set, give us every row that satisfied this condition and every column with no condition on that. So the only row is row 51, participant 51. They had 526 tweets, and that's their anxiety score and their age score. So we can check if that is an extreme outlier. And again, I'm going to keep using the rule of thumb of 3 standard deviations above or below the mean. You can pretty safely use that, but as I've kind of beaten to death at this point, there are many ways to define what your outliers are. You can kind of make that decision for yourself. I'm using 3 standard deviations above the mean. So let's see if this extreme point was higher than what I'm calling extreme limit. Extreme limit equals mean plus 3 standard deviations for tweets. So give me every row where the number of tweets is greater than extreme limit. And we get no rows because we can even type right into the script here, extreme limit, and we can see what that number was, and it was 551. So this number of tweets, 526, was not above our extreme limit. We don't have any outliers. We're all good to go. All of our variables are free of outliers, free of impossible values. We can check our last assumptions and then make our regression model. Someone DM'd me, what level of comment should we include in our R script for the assessment? Yeah, any level of comments that lets us know what you're trying to do with any line of code is fine. You definitely don't have to get into this like really narrative comment style that I get into for class. Just let us know, like, if you're like run histograms, check, like use boxplot to check for potential outliers, screen this point to see if it's an outlier, get descriptive statistics, run a whatever test you're going to run. Something like that that's just very matter of fact and tells us what the next line of code is meant to do. That's fine. You don't have to be telling a story and making jokes the way that I do. You won't get any extra credit for making jokes like I do. I'll actually see that as a threat that you're trying to upstage me as the funniest person in this class. No, that's completely fine if you want to get narrative. I always enjoy when students do, but you absolutely don't need to. So that's all of those. Let's make our scatter plots. And this is just to check for the relationships between each variable. This is just to make sure that none of our variables have like a clear nonlinear relationship, like a parabolic relationship or a exponential relationship or like sinal relationship or something. We want to make sure that either it's like a line or it's just no clear pattern. So let's look at the scatter plot for first tweets and anxiety, and that looks linear to me. It looks like there's probably a negatively sloped line that describes that relationship. Let's look at tweets and age. That looks kind of patternless to me. Maybe it's a positive linear relationship, but it's certainly not some clear other relationship, so that's fine. And let's just check if our 2 predictor variables have any relationship between them. And that looks pretty patternless too, so that's fine. That was kind of to help rule out multi-collinearity. We wanted to make sure that they're not like perfectly correlated, just like we were saying in the lecture, but let's also check that. Let's run a quick correlation test between our 2 predictors. And we could do this between every pair of predictors if we had more than 2. But this is just to rule out multi-collinearity. Again, easy for me to say. This is to make sure that we don't have 2 predictor variables that perfectly correlate, because then they wouldn't be adding anything additional on top of one another. So we'll run that correlation to check for perfect collinearity, and not perfectly collinear, so we're safe. It got a little close for comfort there, but that p-value is greater than 0.05. and it's not clear what direction this pattern even is. So it's fine. These are not perfectly collinear. Anyway, even if it was, even if they were correlated, that's fine as long as that correlation coefficient isn't like 0.8 or higher. So even if this was a significant correlation at the level of 0.2, that does not violate our assumption of multicollinearity. We would need like a 0.9 or almost a 1.0 correlation to actually say that these variables are multicollinear. We cannot include them. We cannot include both of them. We can only include one or the other in our model. But nope, that's not the case. These are maybe weakly correlated, probably not even weakly correlated. So we can include both of them in our model quite safely. So we will start by making the same model we had last week. That's our simple linear model. And that's because we're using a hierarchical approach. We're deciding to compare our more complex model that we're building this week against an established model that we know is predictive. And that was our model that only used anxiety scores to predict tweets. And again, this is not a magical name. It doesn't have to be called model.anx. You could call it like the anx model or whatever else. You don't need to have a dot in it. You don't need the word model in it. You could call it, call it Justin. You could name it after me. That would be weird, but you can do that too. Yeah, you can call this model anything you want. I call it model.anx, just so I remember that this thing in my environment is a linear model and that this is the model that just uses anxiety. So model.anx, I saved that to my global environment. I did this line that says, here's what the model is, save it with this name, put it in my global environment. And now that it's in that environment, now that it's saved and has a name, I can run the summary command on it. And this is just the same thing we did last week. This is just the same model that we saw, the same estimates, the same R-squared values, everything. I think maybe I changed the data around a little bit, but this is the same command. If the data is the same, then the output should be the same. And again, we find that this model has about 0.31 adjusted R-squared. So it explains about 31% of variance, and it's significant. Its F statistic, its F test was significant. It was less than 0.001. So we can say that the anxiety model, that using anxiety to predict number of tweets, is significantly more predictive. It makes a significantly better prediction than does the mean model, than does just the simple model of guessing the mean for every single participant. So now let's make the hierarchical model. Let's add in age as a second predictor. So let's make our more complex model. This one I'm calling model.mult because this is my model with multiple predictors. I could have called it model.anx age or model 2 or anything like that. The name is not magical. The command, the model that I'm building afterwards, this LM, that is the important part. So I want to put in anxiety first because that is the predictor we know and that we're comparing against, and then plus age. And then we could do plus any other predictors we wanted as well. So I do model.mult, that heads over into my global environment. And I can again run the summary command. And again, this is the outcome that you saw in the lecture slides just moments ago. I know it's the same output because this is exactly how I generated it for the lecture slides. And we can see that same result that we saw last time, that the anxiety predictor is significant. The age predictor is not significant. But the model overall, if we include both variables, now it explains 32% of variance. So we did very incrementally increase our R-squared. It is still, the p-value is still less than 0.001. So the F statistic test is saying that this model is better than our mean at predicting levels of our number of tweets. That's not to say anything about our simple model. This is just saying whether our model was better than the mean, which it was. And in this case, its R-squared value was just a little bit better than the previous model. So if you're in big data, if you're just throwing stuff at the wall, you're like, oh, I've done it again. I've thrown another variable in there and I've incrementally increased my my R-squared value. I have exceeded the state of the art. If you are in a more theoretical field, if you're in the social sciences, like assume almost everyone in this class is, then that's probably not enough. You actually want to compare these models. You want to do not just the F test on whether your complex model was better than the mean, but you want an F test on whether your complex model was better than this established simpler model. So we have our complex model, we have our simple model, and we can just use this ANOVA command. And I was saying this during the lecture. ANOVA is it's kind of a catch-all command in R. It kind of hides a lot of different statistical tests in there. Depending on what you put inside the parentheses, will help it determine which test you will be running. So when you put two linear models inside the parentheses, it actually runs an F-statistic test. It analyzes the variance between the two models, which it does by running the F-statistic test, the F-test. So just like the F-test at the end of our summary of our model, we get an F-test here with a number of degrees of freedom. This was 97 residual degrees of freedom and 1. Here it was 97 and 2. That's because we have 100 participants minus 2 because there's 2 variables, and then minus 1 more because there's 2 models, and then 1 degree of freedom because there's 2 models, minus 1. You just always do a minus 1 for degrees of freedom. We'll next class after assessment 1 talk about exactly what is meant by degrees of freedom, but this is just it's an indication of how many things you're putting into the model in terms of predictor variables, people, participants, rows, observations, number of models. It factors all of those things in to run your F-test. So it runs the F-test, it finds a p-value greater than 0.05. Its p equals 0.1059. That means that our more complex model, our multiple input or our multiple predictor model, is not significantly different than our anxiety model. So even though we found this R squared was a little bit bigger, that difference is not significantly different than 0. We can't rule out the null hypothesis that these are actually explaining the same amount of variance, that we can't say for sure that our more complex model was better than the simpler model due to anything other than random chance. For that reason, we would say that our overall model, we would say, is significant. It does predict, it is significantly better than the mean at predicting level of tweets, but it is not significantly more predictive than the simple model, than the single predictor model. We would report that F-test as F of 1 and 97 equals 2.66, P equals 0.11. We would report the previous F-test as F of 2 and 97 equals 24.1, P is less than 0.001. So yeah, so I'll repeat that again. So when we ran the first, we made our linear regression, ran the summary function, and that gave us an F-test that compares this overall model, this complex model, which uses both anxiety and age to predict tweets. It's just comparing that to the mean. It's just comparing two models, the complex model and the mean. And it says that, yes, this is significant, that this model that uses both age and anxiety is significantly different than the mean, that it's significantly better at making those predictions than just guessing the mean number of tweets for every single participant. But that doesn't factor in a more simple model that we could have used. So if we then add in our simple model, model.anx, and then compare them in a second F ratio test, now we're comparing two models again, but instead of comparing the complex model to the mean, we're comparing the complex model that uses anxiety and age to the simple model that just uses anxiety. And we're asking again, are these models significantly different? Is one significantly better than the other? And even though they are different, we observed different R squared values for the two models. We said that the complex model did explain just a tiny shred more variance than the simple model. The F ratio test is telling us that when we look at the distribution, when we look at this known sample distribution, the F distribution, and we look at having the number of participants that we had 97 participants with we had 100 participants, we had 2 variables, we had 2 models. When we factor all of that in, then we can we have an understanding based on that known distribution of how likely it would have been to observe a difference between these two models as big as we observed. And we say that there would have been a 10% chance of observing that difference between those two models, the complex model and the simple one, just due to chance alone, based on our sample sizes and the number of models we're comparing. For that reason, because there's a 10% chance of that difference, that tiny little difference, just being down to chance, then we can't rule out the null hypothesis that these models have no difference, that there's no difference in predictive power between our complex model and our simple model. For that reason, we would say that our complex model that uses anxiety and age to predict tweets is not significantly better than our simple model, that we did not detect any significant difference between this and our simple model. And the simple model is simpler, right? That if we want to predict people's amount of tweets, and we can choose between every time we want to predict someone's tweets, running that anxiety test on them, or running that anxiety test and asking their age, even though it's not that big of a lift to also ask their age, it's not that expensive. It's still the case that it's easier to use that simple model. It's also more parsimonious. It's a simpler way of explaining the world. There's less of a chance that random variation is coming in because we're only using one variable rather than two. So we are more confident that the effect we're observing is due to the actual variables rather than just random chance if we use this simpler model anyway. So because there's no difference between the two models, no significant difference, and because this model is simpler, we're just going to stick with the simpler model. We reject our more complex model in favor of that simpler model. And then we also want to get our standardized betas so we can report it in a table like I did at the end of the lecture. So it said just now the histogram is a normal distribution, extremely low. So to the person who was asking about the normal distribution, remember what I said in the lecture? The histograms, the normal distribution of your predictor, that is not an assumption of a regression model. You don't need normally distributed data to use regression. So I didn't much care that we didn't have a normal distribution. I wasn't really looking for it because that's just not an assumption of a regression model. Haley said, if it isn't significant enough, do we opt to use the simple model despite age being descriptive in the way of actually not having an effect? So just in general in science, we always favor a parsimonious model. We always favor the simplest model of the universe that we can. That we always assume that things aren't related to each other, that there's no difference between any groups, that everything's the same until we have overwhelming evidence otherwise, that simpler models are more likely to be correct. And because there's just bound to be more random noise in more complex models. So when we have two models that don't look significantly different than each other and one of them is simpler, we favor the simpler one because it just has less stuff in it. Okay, we would maybe just mention that age, yeah, we would say that age did not have a significantly predictive effect, or we would put it into our table at the end just to help explain. We would put the age at the end to explain what our predictors were, that we want to be honest with the reader about, like, here's all the things I tried to predict that I thought might be predictive, because we would have included age for some reason, right? We probably had some reason to say, oh, I observed that age might be predictive when I was running my first study. So in my second study, I wanted to test this hypothesis that age was predictive. So if our hypothesis includes age, we do want to include that in our final report of our models. We just want to say that the more predictive model was the one that didn't include age. And someone DM saying, what are the two numbers just before the 0.10 value when comparing the simple and complex model? Yeah, so this is full of a lot of information. So this F-test tells you the residual degrees of freedom and the model degrees of freedom. So these are the same things that are reported right here. So that's something to do with how many participants and how many variables you had. This is to do with how many models you were comparing. It also tells you the residual sum of squares. So how much total variance was not explained by this model in the unit of tweets. So if you add up all of the, or in squared tweets even, because it's sum of squares. So if you take every prediction and every observation and find the difference and square all of those, this is that total for the simple model. And this is that total for the complex model. And that value isn't super useful to us, but it's just saying, here's what your residual sum of squares was for this model. Here's what it was for that model. And this is your sum of squares, your difference between these two models. So if you just subtracted that from that, hopefully, don't check my math. Hopefully it would be this. This is just saying in raw sum of squares, in like raw units, tweets squared, how much total variance was left unexplained, or how many total tweets were left unexplained. How wrong were both of your models combined? So this is the difference between how wrong they were. This is how wrong this one was. This is how wrong that one was. And then the p-value is your p-value for the F-test. So this is the F-test. This is the comparison between those two models. That's the point on the F distribution that you observed, and that is the chance of observing that point with these degrees of freedom if there was a null hypothesis that there was no difference between them. You don't necessarily need to know all that. You just need to know kind of how to report it and what it means in a really general sense, that if you had a significant difference on this F test, then the models were different. If you don't have a significant difference, then they weren't significantly different, and you report it like that. Oh, I love when I get a message that says thanks, that makes sense, because as I'm talking, I'm like, I'm just saying words. Who knows if this is going anywhere? So I'm glad that got there. So as you might remember from the lecture, the other thing we want to do when we build that table, we want to report each of our betas in standardized units. So instead of reporting them in the unit that they originally came in, we want to report them in standardized units so they can be compared against each other. In this case, we knew that one predictor was significant and the other was not. So we already know that anxiety is like the more important slope in our model than is age. But if you had multiple significant predictors, then you do want to be able to compare and say, actually, anxiety explained a lot of the variance and age did a little bit of the variance, but not quite as much. But the only way to do that, the only way to make direct comparisons is to put everything in the same unit, to standardize their unit. And this would make sense, again, if you had things that were in really different units. So if you had, shoe size, and that was really predictive, shoe sizes might be really, shoe size is kind of a bad example. Let's think of something even wackier. Let's say the month of the year that you're born, because then the number would only be from 1 to 12. And let's say that explained a lot of the variance in tweets. Well, numbers from 1 to 12 have to be multiplied by some beta to influence the number of tweets. And if it's predicting a lot of the variance, then maybe that number that they're being multiplied by is really, really high. But that number is going to be really, really high no matter what, because you're such a constrained scale for month of the year. You could imagine any different kind of variable that has a different scale. Not only does it have to be in the model scaled for how predictive that variable was, but it has to be scaled for how different the unit was compared to your outcome variable unit. And that's why we do these standardized betas at the end, because we don't want to worry about differences between units. That it's impossible to make these comparisons, and it's really hard to think through what they even mean if everything's in its own unit. That like, okay, 3 anxiety scores and 7 millimeters and 20 minutes times this times that. No. You want everything in the same unit so you can directly compare. So you can install this package called QuantPsych. I already have it installed. Once you install a package once, you can just run this library command. If you don't have it installed, you'll want to run that and then run the library command. It'll give you a bunch of red text. That just means it's working, weirdly enough. It'll give you all these like terrible looking warning messages and looks like everything's broken, but it's actually fine. As long as you get your little caret back at the end in your console where you can type stuff, that means the package installed correctly. And you can run LM beta. So that's just linear model betas. That's get me standardized betas for every predictor variable in this model. And I had 2 predictor variables, anxiety and age. I get my standardized betas. For anxiety, it was negative. So the higher someone's anxiety was, the lower we would predict their number of tweets. And it was quite strong. It was almost 1 standard deviation unit of anxiety per unit of tweets. And then for age, this was a lot smaller, that we already know that age wasn't predictive. It might have been slightly positive. So the older someone was, the higher number of tweets we would predict them to have, but it was almost 0. That we can see now that there really wasn't much predictive power in age at all. That even if someone's age was much bigger than someone else's, we wouldn't significantly alter the number of tweets we were predicting for them based on that information, because this is almost 0. We're almost just forgetting about their age entirely. So that's actually the end of the in-class version of today's slides. So I'll take some questions for a minute. Everything after this like dash, dash, dash is to test some of the extra assumptions of regression models. So if you go ahead and read, especially section 7.7, but the rest of chapter 7, you can run each of these commands. I didn't put comments because I'm a bad person. No, I didn't put comments because Andy Field describes what each of these things are. This is like cribbing his code directly. But you can run all of those and see if it makes sense to you and if it works later on. And I have some pretty descriptive comments for some of these other steps, just to test our assumptions and see if everything was copacetic. Someone said, can we take references from the book and put them in the assignment? You can, yeah. You can definitely cite the book in your results section especially if you're justifying why you used like one like rule of thumb or something like that as compared to another. You don't necessarily need to. Are there any minimum or maximum number of citations? No, there's no hard limits. You'll see from the example that I gave last week, if you saw at the end, they had like a bunch of citations. That was great. But if you have fewer citations, that can be fine as long as you're backing up your points with literature and you're making connections to literature. That it's hard to write a good discussion section without many citations. In fact, you're not going to write a good discussion section if it doesn't have many citations in it. But there's no minimum or maximum. Someone asked, just to be sure, is it up to us which model we wanted to test the predictors and justify the reason behind our choice? Absolutely, yes. So if you're using a hierarchical approach where you are comparing against a previous model, that you're part of your if part of your hypothesis is that my new, more complex model is better than this simpler model from literature or from my previous work or from other observations, then that kind of leads you to using a hierarchical model and leads you to testing your complex model against that simpler model. But if you don't have, if you're in some new research area or a research area that hasn't looked at these particular sets of variables together, then you might be completely justified in not using a hierarchical approach at all, but just using your forced entry approach where you have multiple predictors and you're only comparing that multiple predictor complex model against the mean alone, because you don't have some theoretically driven simpler model to compare against. And yeah, that's up to you as a data analyst, as a researcher, and as depending on what your research questions and hypotheses are. Someone asks, will we be assessed on testing assumptions? Yes, for any statistical test that you run, you should always make clear to your reader that assumptions were met for that test. So if I'm assessing whether or not you checked your assumptions for your assignment, you should tell me in prose that certain assumptions were met, and I should be able to see how you tested those assumptions. So if you tested the assumption of normality by visual inspection, you don't need to show me the histogram. In fact, you ought to not show me the histogram, but I ought to be able to go back into your R code and confirm that you used a histogram to do that. But that's definitely important to always confirm to your reader that you verified certain assumptions were met, no matter what statistical test you're doing and whether you're in this class or beyond. That's always a very important step of a result section of the end of doing statistical analysis. Someone asked a question, making connections in the discussion. There's a lot of research that has used MWL and system usability. In that case, should I mention the other studies while having more of a focus on voice interfaces? Yes, so this is like into the weeds of an assignment, but if you're finding a bunch of literature making some certain other connection and you want to relate that to your finding, that's great to make that connection. You should definitely go ahead and mention those studies, but you can also mention any differences that they might have had with your study if you find them. So yeah, any connections that you make that you find interesting or that you find relevant, that's great. We definitely won't be like calling you up on like, oh, there's this one key paper in the field that you didn't cite. Now, if you write a paper about the system usability scale and you don't cite the system usability scale, we'll probably be a little like confused by that. But there's not going to be like, oh, you analyzed and compared to these results and not these results. That's wrong. No, your discussion is your chance to compare to whatever results you find like interesting or useful. So that's all grand. I tried citing some work from other websites, and even if I've added the references in proper APA style, the plagiarism factor still shows 8 to 9% of plagiarism. That's grand. If you're not plagiarizing, just like we tell you, don't rely on a single tool to make decisions. Like we tell you, don't let the box plot be the one thing that decides what's an outlier. We do not let the plagiarism checker be the one thing that decides what is plagiarism. We read all of these essays, right? If it's exactly like a box plot, actually. If the box plot shows me that this point is possibly problematic, then I go investigate. And pretty much every time I've done that in this class, in examples, I've gone to investigate and found, oh, actually that point is fine. Likewise, the plagiarism checker will show me these essays might be problematic, and inevitably I go check them, and fairly often it's, oh no, the student properly, like they reference this paper, they reference the results, and they rephrased it a bit, and then they put in parentheses, like they used an in-text citation. So as long as you're using proper APA style citation, as long as you're citing what you're paraphrasing, and as long as you're paraphrasing and not like directly copying, or if you are directly quoting, you're quoting and not just copying. As long as you're doing any of that, we are checking by hand, and we're going to say, oh, that's not plagiarism. Like the thing's just a bit touchy sometimes, but just like a box plot, we are ignoring it. We're using it to flag things, but we're not using that as gospel. We are using our own decision making as gospel. When I asked for the discussion part, can we take results from the studies that don't use the exact same scales but have a similar purpose? Absolutely. Yeah, you definitely should. That's a great direction to go in, of saying like, other work has measured these variables in these other ways. So that could be a potential area of future research, or that differences between my findings and these findings could be due to the fact that they use different measurement tools, things like that. So good question. And I think that's definitely something that the example paper did well also. Everyone's DMing me today. I'm sure if you're just like watching the chat and listening to me talk, you're like, man, Justin loves talking to himself and making up fake questions. I should start making up fake questions to make it seem like people are asking me certain things, like, oh, if I bake you a load of cookies and send them to your house with the assignment, will you give me a better grade? I can't confirm or deny that I'll give you a better grade. No, you don't even know my address. You can't send me cookies. No, that was not a real question. Yeah, you can, if you have any further questions and comments, of course, you can email us. Keep any of your thoughts coming towards us. And like I said, please do fill out that feedback form, just so we have the chance to adjust the last few weeks of class and make things a little bit better for you before we're done with QDA for the year. It does help me as a teacher also, and that's important to me in general, just like getting better at this whole thing. Will we be assessed based on the complexity of the method to remove an outlier? No, I will say, again, I keep saying, maybe people didn't get an email update for this. Maybe I posted it weird, but you should definitely check out the announcement that I made at the end of last Thursday's class. It was called like on problematic data or something like that, some pretentious name. We're not looking for you to have used like the right way TM. Like there's not like some perfect right way to deal with problematic data that we're checking that you use. We're looking to make sure that whatever method you use to deal with any problematic data, that you justify it to your reader, to us, that you're explaining, here's what I did and why I did it. That I don't care which method you use, as long as you explain kind of why you did it, what your decision-making process was. When we make this class in person sometimes, you're gonna have to come to my place because I'm not coming to your place. If you guys, maybe the tutors will consider arranging some kind of that was a joke. You're not coming to my place. I work from home these days. I don't like coming into the office. If you want to have some kind of in-person get together, I'm sure the tutors could consider arranging something for QDA. In general, if you're in like the MSc and HCI thesis, I think in the second half of in the spring term, while you're like working on theses, we will have some like in-person get-together type days and some like special, like last year we did like HCI master classes where we taught like some specific skill for an hour or whatever. We will have times to meet together in person, but this is like a Justin personal thing. I don't like coming in anymore unless I like absolutely have to. So as much as I love teaching this class and as much as I like you guys, I probably won't be around in person. Maybe, I don't know. If I am, I'll let you all know well in advance. But yeah, there's just not a great place to put everyone is definitely one problem. And my general aversion to being around people is the second problem. So if we can solve both of those, I'll let you know. I'll probably be on campus. I'll have to be on campus at least once in this in the spring or the summer, because I will be submitting my PhD thesis eventually. So I'll get a chance. I'll let you all know where I'll be for that. So if you want to come throw eggs at me and say, how dare you have made me learn statistics, you'll have a chance for it. That's also what we found. So the reason we do this online is not just that I hate being around other people. It's because we always do an end of year feedback form as well, end of year, what do they call it, like module assessment or whatever, where everyone rates how good or how much they like the module. And after like many years of this class being completely in person, the feedback was always like middling, fine, this class is grand. And then once we went online because of the pandemic, everyone was like, this rocked, everything went really well this year. Like the feedback went way up by being online. So we were like, man, between trying to fit everyone in one room and like delivering something where it's like, here's some code, like go do some live coding, it became a lot more, we figured out that the class was more successful online anyway. So between me not wanting to be there in person and the class being more successful online, this just worked. Anyway, enjoy your reading week. Good luck with assignment number 1. Keep your questions coming in the form of emails and smoke signals. And I'll see you in a couple of weeks. See you later.